Alrighty, let's do this. In this video, we are going to learn about how to create shear diagrams. So last class, we learned how to find reactionary forces. So in simple terms, that means that if you have a beam and there is weight put on the beam, I can calculate exactly how much each support of the beam is holding up. So force is getting pushed down, both sides are pushing up to counter it. I can tell you exactly how much each side is supporting. This lesson and next lesson, we will begin to learn about beam failures. What makes a beam fail? Well, basically, a beam can essentially fail in one of three ways. In this course, we will learn two of those ways. The first method of failure is what we call shear failure, and we're going to get the introduction of that in this lesson. Shear failure is essentially the force applied is so strong that the beam will just snap in half. Method number two of failure is a moment failure, and we're going to learn that next week. A moment failure is the beam is bending too much and then it becomes unstable. The third method of failure, which we will not learn, is called torsion, which is twisting of an I-beam. So shear force, let's talk about that a little bit further. Shear force is load that is applied vertically, straight up and down. We calculated shear force last lesson, so you are familiar with shear force. Shear force is the load being applied down, and then the reactionary force going back up. Both of those are shear force. Shear force failure occurs when the load is just too much for the beam to handle and just snaps. When we analyze a beam, and this is a pretty important bullet right here, when we analyze a beam, we are interested in the maximum shear force the beam will see, since if the beam did fail from shear, it would occur where the shear force is maximized. So we care about where the maximum shear force is and where it occurs. Therefore, we will determine the shear force at every point along the entire beam span by drawing what we call a shear diagram. So we will map out all the shear forces along a beam, and then once we have that done, we can determine the maximum. So let's go to an example, and I'll teach it via an example. So I will ask you, okay, draw the shear diagram for the following beam and find the maximum shear force this beam will experience. So here it is. We have the forces going up, forces going down, and you will first have to find the reactionary forces, which you should be able to do by now. Sum of forces in the y is equal to 0, so the 8 and 11 going down is equal to the reactionary force at A plus B going up. And then we'll analyze a point for the moments. We'll do point A. So if we analyze point A, force of A, it has a distance arm of 0, which is 0 multiplied by out. 8 times 5 plus 11 times this distance is 9 is equal to this force times 20, and we get F of B is 6.95, and F of A is 12.05. Okay. A shear diagram is essentially a graph, XY. So you know your little XY graph, you have your Y going vertically, your X going horizontally. The X-axis of the graph is the feet along the beam, and the y-axis is the amount of shear. So let's look at your free body diagram. You have your y-axis is the shear, your x-axis is the feet. So here's your graph right here. Again, y-axis is your shear force, both positive and negative, and the x-axis is the amount of feet. So we'll say that each of these boxes is 1 foot going across. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then another 10 is 20. line up your shear diagram to be exactly underneath your free body. So we start here and we end here. We want everything to be lined up perfectly, and that'll make more sense why later. We will start at point A and move along the beam and map out the shear at each point. And each time a new force appears, we will add or subtract the shear amount. Okay, so let's start at the origin. Right away, we have a shear force of 12.05 in the up direction. So I'm going to write that as a positive, which is going to be a point right here. A point at 0, 12.05. That means that the shear force at x equals 0 is 12.05 kips. My mouse. Then I will keep moving along. And as an FYI, by the way, this is only a diagram when you do this, so you don't need to be precise with scaling. You can just eyeball it. I made this with a grid to be more precise, just for the sake of introduction. Okay, so we will put your pencil at the point 0, 12.05 and move horizontally until a new force appears. So I'm at 12.05 and nothing's happening, nothing's happening, nothing's happening, nothing's happening. Oh, boom, right here at 5, something happens. What happens? I have a shear force pushing down of 8 kips. So we were at 12.05 kips. Now we're going down 8 kips. So what's the shear force at x equals 5 feet? It'd be 4.05 feet. Therefore, the shear force at 5 feet is 4.05. Then what happens? Well, I'm going to keep going in a straight line. Nothing's happening, nothing's happening, nothing's happening, nothing's happening. Boom. Right at 9 feet, something else happens. What happens at x equals 9 feet? I have 11 more kips of force going downward. So I was at 4.05, and I'm going to subtract another 11, putting me at negative 6.95. So now I'm at negative 6.95. So the shear force at x equals 10 feet is negative 6.95. The shear force at x equals 12 feet is negative 6.95. And I'm going to keep going at negative 6.95 until I see another shear force. And that next shear force occurs at x equals 20 feet, and that'll be the reactionary force of B. And that will go up 6.95. So I was at negative 6.95, and then I went up positive 6.95, bringing me back to 0. So notice how the shear diagram starts at 0 and ends at 0. And if you calculate the area under the e's, they should be the same. So we have completed the shear diagram. Not too bad, right? Here's your shear diagram, just drawn in simple terms without the grid. Again, you don't have to draw the grid when you're doing this by hand. They were only there for reference. So I might then ask you, okay, what is the maximum shear force that this beam will see? And the maximum shear force can be either positive or negative. It's the largest absolute value. So the largest shear force would be at 12.05 kips, which occurs between 0 feet and 5 feet along the beam, starting from point A over here. So between here to here is the largest shear force. Okay, let's do another example. I want you to draw the shear diagram for the following girder and find the maximum shear force this member will experience. So I have a 24-foot girder, and I have 5 kips going down, 6 kips going down, 8, 6, and 5 going down. Each of these are 4 feet apart, so 4, 8, 12, 16, 20, 24. And in this case, I gave you the reactionary forces. I won't always do that, but sometimes I will. Depends on how nice I'm feeling, which is usually not very nice. And I want you to be able to draw the shear diagram from here. So before I show you what the final answer will look like, let's talk it through. Again, you start at x equals 0, and each time you see a new, you go horizontally until you see a new force. So right from the beginning, 15 kips going up. So 15 kips going up, then I'm going to go over in a horizontal line, and then at 4 feet, I'm going to go down 5 feet. 4 feet later, I'll go down 6. 4 feet later, I'll go down 8. 4 feet later, I'll go down 6. 4 feet later, I'll go down 5. And then at the end, I will go up 15. So let's see what that looks like. Okay, here's the shear diagram. We start by going up 15, and then we go across 4, and then we go down 5. So 15 minus 5 is 10. Now I'm at 10 kips, and then I go down 6 kips at 8 feet. So 10 minus 6 is 4. I go down another 4 feet. Over here at 12 feet across, I see an 8 kip drop. So 4 minus 8 is negative 4. Again, continue on for 4 feet. I go down 6 kips, brings me negative 10. And then at 20 feet, I lose another 5 kips, which brings me negative 15. And then at x equals 24 feet, I have 15 kips going up, which brings me back to 0. And I think that's a good starting point for this video. On the next lesson, we're going to learn about how to do shear diagrams when we have distributed loads.